So Naoko is a highly accomplished physicist. She was one of the first to see the ultra high energy neutrinos in IceCube while she was at Wisconsin. And she's been leading all of IceCube's big accomplishments that you've been hearing about in the news, and leading us, the whole community, into the era of multi-messenger astronomy, and us being able to do astronomy with neutrinos. She's had many adventures, racing electric cars in the desert. She's deployed neutrino detectors in the Bahamas, at the South Pole, and most recently off of the coast of Vancouver Island. Today we're going to hear about her work on the most recent release of IceCube data, and she basically mapped the Milky Way using neutrinos. So without further ado, please welcome Naoko.
Hi. Thank you for the generous introduction. Is my mic okay? I just fidgeted and then figured it out, I think. Okay, so I'd like to start by telling you that this is a, okay. I'm gonna come over here. I'm a very animated speaker, so I'm just gonna be in front of you and animate. So this is a picture at the South Pole. This is where our computers are housed for IceCube. Of course, the detector is under the snow, but this is where all our computing happens. And I like this to start with this picture because it has two features in the sky that I really like. First, this green thing. This is the aurora australis, or southern lights, right? Very pretty. And then this big feature in the sky, which is the Milky Way, of course. And today's talk is going to start with the Milky Way. So this is an iconic image of the Milky Way in many different wavelengths of electromagnetic radiation. So we start off with radio, where the wavelength is longest, and then you go to shorter wavelengths or more energetic photons, depending on how you want to think about it. And we end in gamma rays here. And this is, NASA has this beautiful poster of this with many different editions. And if you go give this talk at Goddard, they can tell you which edition the posters are and things like that. So it's a very iconic image that we've been seeing. So what is, just for those of you who are not astronomers, as I am not, what are we looking at here? So we are here. This is our spiral galaxy. This is the Milky Way. This is the galactic center. We're here where the sun is. We look this way towards the plane. The plane is a pancake, right? It's flat, but it has some bulge in the middle. So if you're here and you look that way, you see this cross section of this flat circular thing. That's what you see here, and you straighten it out. And that's what those images were, taken at different wavelengths, right? So for the first time, we announced that we see the galactic plane, or the Milky Way, in neutrinos. This is the first non-electromagnetic view of our own galaxy. We had a press conference in June, I think it was, at Drexel. We were in Science. We had a New York Times cover. We had a lot of press. So today, the first part of the talk is how did I get here, right? And then I'll zoom out and talk a little bit more about neutrino astronomy and multi-messenger astronomy in general. So I like to start with this talk, with every talk, with the highest energy particles, right? So my high energy is maybe not your high energy, or your high energy is probably not my high energy, more like. So what are we, I just realized that's the camera, and you can just see my butt, okay. Gotta be careful. Okay, so here I made an energy line, and today I'm going to talk about TeV and PeV. So those of you who are not used to this energy regime, this is 10 to the 12 eV to 10 to the 15 eV. Okay, the highest energy charged particles we've created is at the LHC in the Earth's rest frame basis, and this is like tens of TeV, right? The highest energy particles that the universe has given us at Earth is in the form of charged nuclei. This is ultra high energy cosmic rays, and they extend above 10 to the 21 eV. The highest the highest energy neutral particles are gamma rays, which we can distinguish to maybe like a PeV, and then at tens of PeVs, we have neutrinos. So how are these connected, right? If we wanted to make a neutrino beam on Earth, what we do is accelerate charged particles, hit it on target, filter things away, and you get a neutrino beam. So could it be that you accelerate nuclei, it interacts somewhere in the universe, and we get very high energy neutrinos? Things that produce high energy gamma rays could be a decay of neutral pion. Now, wherever there's neutral pions created, there's charged pions created, and that decay produces neutrinos. So are these two connected? Are these created in the same places in the universe? That's the kind of questions that we like to ask. So now that galactic plane is now not just a little ribbon here, but the whole sky with the galactic center in the center here. And here's a log-log plot of energy versus distance in terms of messengers. So at low energies, you have microwave, which is, long wavelength, right? And then you go optical, X-ray, gamma ray, you're getting into higher energies. Now, at some point, electromagnetic radiation stops being the best candidate of messengers because at these high energies, the gamma rays interact with the leftover light from the early universe. These are cosmic microwave background and infrared light background. So here we are, we see the, I think it's an E plus E minus peak that you see here. Anyway, this means that at some distance and some energy, photons don't travel through to us anymore, right? At very high energies. Now, we know from the first slide that cosmic rays goes high up, 10 to the 21 and above. So we know there's stuff happening in the universe at very high energies, right? However, cosmic rays are charged. So let's say there's a black hole or something here, and it produces cosmic rays. There's a lot of magnetic fields in between me and that source. And the cosmic rays may not travel in a straight line. So if you see the cosmic ray here on Earth, you would point back and you'd think it came from this way. So it doesn't point back to its source. So this is a rather old plot of high energy cosmic rays, but if you assume that the cosmic rays are proton rather than iron-like, so they don't bend as much and they come very close by and these are extremely high energy, then maybe you can think about localizing it to where it comes from, and it's very hard, and we haven't localized anything yet. So you can't quite resolve things in cosmic rays. You can resolve things in light because light is neutral. So neutrinos can exist in between here. Neutrinos not only bridge the energy gap here, but it bridges the resolved universe and the unresolved universe. And this is the whole idea of neutrino astronomy. Okay, until 2013, neutrino astronomy was really a dream. And I have an asterisk here because, of course, there were things that we have seen in neutrinos that are astrophysical objects. The sun and supernova 1987A. Supernova 1987A was not a directional detection. It was just timing, right? Flux went up at the right time. So it's not that we haven't seen any astronomical objects. It's just that they were low energy. So we're talking MeVs and KeVs here. And what I call astronomy, neutrino astronomy, I'm going to talk about PeVs and up here. So with that caveat, what happened in 2013? So we had this argument. We've been making this argument that neutrinos can fill the gap. It's the fill the gap in energy, fill the gap in resolved and unresolved forever. But we haven't really seen a single neutrino from outer space yet at these energies. And that changed in 2013. So we did a lot of press back then too. But what happened was this. So this is the discovery of diffuse neutrinos, diffuse extragalactic neutrinos. And we got the cover of Science that time too. So first of all, let me before I talk about this plot, let me talk about why it took so long. Because IceCube was starting construction much long before that. And I think we completed construction in 2011. So this was 2 years after full construction was completed. So why did it take so long? So IceCube is really a particle physics detector. It's not really a telescope per se, in that the data is really hard to understand. So for every astrophysical neutrino, this is a neutrino that comes from outer space, right? We have 10 to the 9 atmospheric muons triggering our detector, and 10 to the 3 atmospheric neutrinos triggering our detector. These are our backgrounds. So to the first 9 orders of magnitude, everything is background in IceCube. And that's why it's hard to do neutrino astronomy. So every analysis is a fight against background. So what happened in 2013 is that we found a way to suppress this background quite harshly. And this is, again, a log-log plot, energy versus events. So the count of events keeps going up in energy, whereas if you only allow these backgrounds to be considered, it should have gone down. And this is the first time we said, okay, these neutrinos must be coming from outer space. So my role back in 2013 was to figure out where. And this is what I did. And this is the plot I made back then. Everybody hated this color scale. And you'll see this is a theme in IceCube. We keep changing color scales. Anyway, before we understand this plot, let's talk about the detector itself and what the data is like. So the detector itself, again, that was that counting house, the computing house that I showed in the first picture. That actually sits on top of 2.5 kilometers of ice. So at IceCube, you're at high altitude when you land at the South Pole. Below it is over 5,000 PMTs, essentially, catching Cherenkov light, right? If you're buried 1.52 kilometers under ice, it's black, pitch black, there's no light, and then you see particles, Cherenkov rating. So this is like any other particle physics detector. Here is an event. So here, red is early and blue is late light. And the amount of, the size of the circle corresponds to the amount of light you saw at that particular PMT. So you see more light seen here than anywhere else. And you also see that there was something that emitted light that went like this, and that's a muon. And so we know, and we actually know this is a neutrino-induced muon, because if it went this way, right, it must have come from this way. There's a lot of bedrock and earth and atmosphere. And if you were a muon that got created in the surface of the earth, you would not travel all the way through. So we know it was a neutrino that came, interacted somewhere before our detector, turned into a muon, and then a muon went through. And that's how we collect events. This is the only technical thing about this talk, but I do need to go through this. So what I just showed you is called a track event, and it's caused by muons. It could be caused by atmospheric muons created in the atmosphere from cosmic ray air showers, or it could be caused by neutrinos, muon neutrinos that went through charged current interaction and made a muon. Either way, it leaves a track. The other thing neutrinos can do is to make what we call a cascade event. So these are particle showers. If it doesn't look like a particle shower because you're used to a beam of shower of particles, and it actually is going to be a beam of particles in there, actually, a shower of particles. But what happens here is that the shower length is small compared to the string distance, but the light radiates out. So for IceCube, and I'll get to this point later again for various reasons, but in IceCube, the optical scattering distance is short, but the absorption length is long, which means that photons, light is long-lived, but it scatters a lot. So you don't preserve the information of that particle shower, because if it did, it would be a nice light emission cone, right? But it's not because of the scattering length. However, it makes it out, and because this is a high energy shower, you get a lot of light from it. This is a kilometer by kilometer by kilometer, just to give you a scale. So that's a huge region where light was seen, right? So this happens when the neutrinos interact not by charged current interaction, producing a muon, but by any other interactions. So these are the two types of topologies that neutrinos can leave in IceCube. And you can already tell this one is better to point back at, right? You can see that, okay, something went this way, it must have come from here, come from there, right? Something on the sky over there made a neutrino. This is a little bit challenging. So this one we can do better than 1 degree usually. This one, greater than 10 degrees on the sky. So this is me saying this event could be a neutrino that came from here plus minus 10 degrees, right? That's quite a big patch. However, the energy resolution is good here because you see all the energy deposit contained within the detector, whereas this one, you have a particle that comes in that already lost some energy and goes out, losing energy, right? Okay, so again, this is the only technical thing. I'd love to stand in front of this camera. This is the only technical thing. So in IceCube, ever since 10, 15 years ago, we've only used track events to try to point back at the sky. So here is our 2008 data. This is quite old. Back then, we only had a half-complete detector. Back then, we observed 37,000 track events. We put a dot on the sky for every direction it came from. And then we said, okay, is there clustering? I'm looking for a source here, right? Except we can do better because we have angular resolution for each event and the energy, which discriminates a little bit from background. So we took that in, we do a likelihood analysis, and we turn it into a p-value map. And this is what that looks like. So that turns into this. Well, this is an updated version. This is the 2020 version. But you can see we looked at the hottest spots, and here are the northern sky hottest spot and the southern sky hottest spot. We calculate a p-value. Now, a p-value for us is the % chance that a random fluctuation would cause something this signal-like. So 10% means that 10% of the time, a random background fluctuation would look like this much like signal, which is quite a bit. So this is background fluctuation, obviously, right? If it happens 1 in 10 in background-only maps. Okay. So let's come back to this, the 2013 analysis. And this is the sky map I produced back then. And besides the color scale changing on you, you can see, I just need to figure out a place to stand. You can see that it doesn't look anything like this, right? And that's because when you reduce the backgrounds quite harshly, we were left with a lot of cascade events. So first thing first, this was not a lot of events because we were doing a discovery analysis and we cut as hard as we can to get rid of background. So very few events, but also each event is quite large in angular error because they're cascade events. But I learned something that time. I said, okay, well, if you want a signal-rich data set, it's gonna be cascade events. Why don't we do source searches, localizations on the sky with cascade events? Now, nobody thought this was a good idea back then. We had been, and still to this day, and still until this galactic plane analysis was unblinded, we continue to do source searches using exclusively track events, because why would you blur yourself to 10 degrees on the sky, right? But I thought I had a shot at this for a couple of reasons. So first reason is suppressed background. This is really the key. So again, backgrounds are atmospheric muons and neutrinos. These come from air showers, cosmic ray showers, particle showers. And remember, the muons make tracks, right? And this is 10 to the 9 times signal. So this is our dominant background. So if we don't take tracks, we don't take this dominant background. So we can filter out a lot of the background. Now, again, it's 10 to the 9 higher. So if you have like 10 to the 1 and 10 to the 9 edge cases, you're still gonna be messed up, which we still have to account for. But this was the biggest background reduction you can do. On top of that, actually, atmospheric neutrinos get suppressed too for a couple of reasons. But the one I can explain with this plot is that atmospheric neutrinos get created at the same vertex as the muons. So in high energy showers, these are very collinear and they come together to the detector. So a lot of times the background neutrinos, the 10 to the 3, are accompanied by the muons. So if you filter out tracks, you filter out these background neutrinos too. Okay. So yeah, of course.
Like the cascade version, how many do you get per second, per day, per?
Yeah, so our trigger rate is 3 kilohertz, and it's on 24/7, 365 for over a decade. Again, 10 to the 9 of that is background, and then a further 10 to the 3 is background. So whatever's left, actually, I'm gonna get to this point, but the signal is actually cascade rich. So whatever's left is actually cascade rich. And if I don't explain it in the next slide, let me know. Okay, so when you get rid of such an enormous background, what happens is you get to lower your energy threshold, which is very important for softer sources. But let's talk about that signal. So, sorry. No, I'm sorry. I don't know where to, I want to be where the desk is the problem probably, I'm sorry. So astronomical sources create neutrinos in whatever flavor they create. But because it's created by many different sources and it travels over many different distances, at Earth to first degree, it's a 1-to-1-to-1 flavor ratio that we expect. Now the background is almost all muon neutrinos from the atmosphere. So So we're saying that, okay, electron neutrinos create cascades, tau neutrinos create cascades, muon neutrinos create tracks and cascades. So half the times it creates tracks, half the times it creates cascades, right? So there's 6 interaction patterns and only one of them creates tracks. So by suppressing tracks, you're only killing 1/5 of your signal, and you get all this background reduction. So this is what we traded for inferior pointing, right? So, and again, nobody believed this was a good idea. But I had some tricks up my sleeves, right? So first, if you're not looking at a point in the sky, but a large feature in the sky, like the Milky Way, right? It doesn't matter if your vision is a little bit blurry, you can still see it, right? If you wear glasses or contacts and take it off, the first thing you start losing is small things, but big things in the sky you can still see, right? So we don't want to go after point sources, but we want to go after some very big feature in the sky. The next thing is that I wanted to improve these cascade pointing. So I asked for that, and then I got a grant to do that in 2017. And it's a good thing these reviewers believed me, because my collaboration didn't think this was a good idea. But I'm stubborn. So I kept doing it. I roped in a very good postdoc. So this is an awful plot for many reasons. First of all, I reversed the color scheme on you for early to late, right? Now blue is early and red is late. Why did we do that? I have no idea, but this is the official plot, so I have to show you the official plot. So each circle is, again, a PMT with how much light it saw. Okay, at each PMT, and remember we have over 5,000 PMTs, we record the waveforms of the light we saw. Now the waveforms here are in black. Those are the data points. If we fit a particle shower that went this way, the red arrow direction, we would have expected these waveforms, and we do this for all 5,000. And if it was completely the other way, I don't know if you can see the blue arrow here, then the waveforms should have been this, right? So for 5,000 PMTs, we have whatever, 10 digitized waveform plots, right? And for every direction we can think of, we can generate what each PMT's waveform should look like. So this is a very good problem for machine learning. So we trained a neural network to recognize and do the reverse problem, right? Given that these are the waveforms we saw, what is the most likely direction of that neutrino or that particle shower that the neutrino caused? Okay. And Mike was a really good programmer, and he was very much into neural nets, so this took off. And then the other thing I had was another student that I roped into, Steve Sclafani, who's now a postdoc at Maryland. We improved event selection. So I said that 2013 discovery analysis, we had to do pretty harsh cuts. We didn't need to do such harsh cuts this time because we're looking for a large feature in the sky. So some background's okay, right? The way I like to think of it is if you're in downtown Los Angeles with a lot of light pollution, but you're trying to look for the blurry image of the Milky Way, right? Some light pollution you can tolerate, not a lot, right? So this is the analogy. So what he's trying to do is suppress background while keeping signal. And he suppressed background enough while keeping signal such that, so if you're a particle physicist, this is the effective area of the neutrino per energy for the event selection that he made. This is also neural network based too, actually. And you can see that tracks only get this much signal. The first version of the cascade analysis we did is the blue, and the second version is dark blue, or maybe it's black. And for those of you who don't do effective areas, this is how many astrophysical neutrinos from the galactic plane we would expect in a year versus energy. So this is per bin, okay? And so if you are just using tracks like we have been forever, you only expect, for example, at this energy bin, you only expect like 0.2 events per year. Our first attempt at this was 1 event per year, and our second attempt was like 4. So we're getting better at keeping signal while suppressing background. And with those two, this is finally what we did to see the galactic plane. So here, I have also done one more horrible thing. This is the last thing. I have changed coordinate systems on you. This is an equatorial coordinate. So now the middle is not the galactic plane. The galactic plane is this UV-shaped thing here. Okay, so the name of the game is to see if the hot spots correlate around the galactic plane. Okay. 2017, we did this when we asked for funding. We did this proof of concept analysis using 2 years of data. And we said, oh, the p-value is 65%, meaning only 65% chance that well, a lot of chance that the background can fluctuate to be the signal-like. 7-year data, this was published in 2019. It's getting 2.1%. Again, nothing to write home about. 2.1% of the times it fluctuates will look like this, right? Finally, for 10 years of data, with the improvements that Mike and Steve made, this is 0.0004% chance that a random fluctuation would cause something that looks like the galactic plane. In other words, it was a 4.5 sigma result. And that's what we published. So let's talk more about this. So this is, again, we're back to the strips. This is the optical view of the Milky Way. This is gamma rays. This is the highest energy, right? So this is the best counterpart we have. This is still in GeVs or MEVs to GeVs and not quite TeVs. So it's not that strong of a match. But from here, we can say, okay, of these, which one came from the pi0 decay that produces gamma rays? Because that's a template for any pion decay, which means it's the neutrino component. So here is the predicted neutrino sky from the gamma rays, right? And then again, we used cascades, which is very big. So here, you blur it by this bigness. That's what you should be seeing. And finally, this is what we saw.
Just to be clear,
yeah.
All the gamma rays that you see came from, turned into pions?
So from here, the model teases out what part of this was from pion decay. So just the pion component of this gamma ray. Yeah, and that's this. Correct. Source subtraction, leptonic processes filtered out. Yeah, absolutely. Okay. So, yay, we found it. So now everybody in the collaboration wants to use cascades to do source searches, you know. Okay. This is a picture that Jim Madsen, who's at the University of Wisconsin-Madison, sent me. And he said, because I used to be a Wisconsin postdoc, he said, every time I walk by your old office, I see your old poster and think about this. And so this is the first ever diffuse neutrino search from the galactic plane in IceCube that I did. And I think 2012 or something like that. So full circle, I'm back. We have seen it. It has worked. So sometimes it takes 10 years to prove a point. And you know, you just have to tell your collaborators that you were right after 10 years. Okay, now that we see it, of course, this is the question, right? So here, again, the multi-wavelength, and again, the neutrino data, it's a little bit wider because we're blurrier. But we only tested that template from gamma rays, but we didn't independently measure this. So, you know, are there point sources mixed in, right? Gamma rays had to subtract sources, known sources in gamma rays. We don't have known sources in neutrinos, so we didn't subtract anything. And there were no significant point sources in the neutrino data. But is there going to be resolvable point sources in there? Which ones? And how much do they contribute? Maybe this is all point sources. Maybe there's no diffuse emission from the galactic plane. I don't think that's true, but it's possible, right? We can't rule it out yet. What's the energy spectrum? So I didn't talk about this at all, but the energy spectrum of these, we also used a template and we said, does it match or no? But we need an energy flux measurement independent from templates, and we are working on that. What template discrimination? We used gamma ray based templates. Is that the right thing to use? Should it look different? Does it look different, right? And how does it compare to different wavelengths? Like by eye, you might be able to see some features that look suspiciously similar in different wavelengths and some that are missing suspiciously, right? What does that mean? Is that real? Is that statistically significant? Well, not yet, but will it become that, right? So once you see it, you can start asking all these questions. So that's the first part of my talk is about seeing the galactic plane and neutrinos for the first time. And the second part, I'm just going to zoom out and talk about the neutrino astronomy context here. Yeah, of course.
To wrap my head around
the
previous image.
Yeah.
See that P there in the center?
Yes.
What kind of numbers are we talking about? How many cascades.
Yes. So,
Okay.
no more. No, less. So the whole data set is like tens of thousands. And so I don't know the number off the top of my head, but I think it would be in the tens or like 100. Now, the thing is, it's not a statistically significant point source, so we can't claim anything.
On similar lines.
Yeah.
What fraction of your individual cascades do you assign to the Milky Way if it's not in the plane?
That's a
very large fraction. It's not planar.
Yeah.
What you see in the gamma ray.
Yeah. So that's a very good question. Let's see. So this is okay. So the straightforward answer is like less than 1%. The more complicated answer, which I think you're asking me, is how much percent of the data can you attribute to this, right? And to, as opposed to extragalactic or like background. And that's a fit that we're still working on, because depending on the background assumptions, how much background you let in and how much you didn't, and the extragalactic component, which is not trivially characterized, like depending on which analysis you ask IceCube, they have different flux and gammas. So depending on those, that answer kind of changes. At our most sensitive energies, which is about 70 TeV, we think the extragalactic to galactic ratio is like 10 to 1. Yeah. But then again, that's at 100 TeVs. Okay, so let me zoom out. So let me first talk about the evolution of IceCube results. So this is kind of a cute infograph that the comms people put together. So IceCube was completed in 2011. 2013 was that discovery that I told you about. And then first source, 2018, this is the TXS 0506, which we claimed was a flare. And then here's a particle physics result, but let me skip that for now. And then the second source, this is a steady emission source, we think, NGC 1068, which is a nearby starburst galaxy. This is a far away blazar. This is a nearby starburst galaxy. And then, of course, we saw the Milky Way now. So first of all, our pace of discovery is accelerating, so that's good, right? Second of all, we only have maybe 3 sources that we can identify as high energy neutrino sources. So even though I don't do neutrino astronomy in air quotes anymore, we are far from where we want to be. Let's talk about the global landscape. So here are planned or already built neutrino telescopes around the world. So IceCube is at the South Pole. Baikal in Russia, Lake Baikal has been running for a long time. And then there is KM3net, which is the successor to Antares, which was running for a long time in the Mediterranean. There are new efforts. Trident is the Chinese version of IceCube. And I should not say that probably, that's probably offensive. And P1, as Reina said, is a new endeavor off the coast of Canada in the Pacific. And right now it's a Canadian, US collaboration. I'm involved in these 3 things. So IceCube, we want to make it bigger. So red is the current footprint of IceCube, and we want to make it blue, right? So we want to make it by volume 40 times bigger. And then KM3net, which is the one in the Mediterranean that's being built, is a water detector. And then P1 is also a water detector off the coast of the Pacific Ocean. So, okay, let's talk about why we need so many, or my argument for that. So here is all the neutrino fluxes in one plot. And this is from over 10 years ago. And it's a little bit wrong, but it doesn't matter for the point I want to make. So I'm just going to go ahead and doctor it, okay? I care about this energy range, and I've simplified it to 4 straight lines, right? So here's flux versus energy. This is multiplied by E squared. So again, a straight line here is a steeply falling line, and without the E squared, okay? So they're all steeply falling, and you multiply E squared to even it out so we can see features. This is the atmospheric background. This is the thing you want to get away from. There wasn't even galactic back 10 years ago, so I just drew that line in by hand. Extragalactic, and then above it is what people call GZK or cosmogenic. These are from the ultra high energy cosmic rays interacting with the microwave background. There should be a flux of neutrinos there. So these are the 4 different populations of neutrinos, okay? And what I want to get at for this plot is, I mean, the fluxes are probably wrong by, you know, an order of magnitude or whatever. But what I want to get at is that the spectrum, the hardness changes, right? So atmospheric is soft, then galactic, extragalactic, GZK, right? So depending on what you want to measure, what you need is different. So this is a thing to combat. Galactic, you are very close to the atmospheric background. So your energy discrimination doesn't help you as much. But that means that you need good pointing. So you want it to be good pointing, a telescope that points well, that's in the northern hemisphere, so you can get away from backgrounds to see the southern hemisphere better. But smaller is okay because you have abundant flux here, right? Then there's extragalactic. Now you're getting harder, so the energy information helps discriminate against the background. You're separated more, right? But it's rare, so you need a larger detector and you need pretty okay pointing still to resolve something. And then there's the GZK. So this is very rare events, right? So you need a huge detector and a signal that travels so you don't have to put your, you know, sensors so densely. And so these are the needs. So, okay, the needs are still here, okay. Water Cherenkov, so this is a simulation of a muon going through water. And this is a simulation of muon going through ice. And you can see that in water, there's not a lot of scattering, which means that you get to point really well in the sky. However, there's a lot of absorption. So you're likely to miss the signal. So you need to densify your PMTs, which means that you can't make the detector that big, right? Ice Cherenkov, so this is IceCube, right? There's a lot of scattering, so it's harder to point, but there's not a lot of absorptions, as I mentioned earlier. So you don't have to instrument as densely. And then there's radio, which is a signal that a Scarian radio signal is something that emits from particle showers. Radio travels. Radio just travels. So you're talking this, I don't know if you can see this, but this is like 10-kilometer scale is here, right? So this is huge kilometers, 100-kilometer scale signal traveling. You can make a very large detector out of this, but the energy threshold is high, and it doesn't point that well in the sky. So different needs, different technology, right? So you can tell galactic is probably best with water Cherenkov. Extragalactic, probably ice. GZK, radio, right? Different needs, different detector optimizations. Case in point, I never thought about joining P1 or KM3net until I saw the galactic plane. And I said, oh no, IceCube or Gen 2 is not going to be that helpful. And this is a great plot to show this. So this is the galactic center. You see the arms. And this is from this archive, by the way. So you see the arms. And here are some maybe galactic sources we want to see in neutrinos. Their distance there's some uncertainty here, right? IceCube tracks what we've been doing for the last 15 years is this. This is how far you can see. IceCube cascades went like this. And you can see we covered more of the arm. This is why it was so much better to do this, because you're not like out here where nothing is. Now, KM3net, that water detector, does this, right? You're finally able to cover the sources and the galactic center. IceCube times 5, this is a proxy for Gen 2, IceCube Gen 2. Even with that 40 times volume, only extends this way, right? So I'm not interested in this way. I'm interested in this way. So as soon as I saw the galactic plane, I said, okay, I need to join a water Cherenkov detector because IceCube's not going to be able to do much more galactic neutrino science. And I think it's not a bad thing to have diverging needs in the field. I think it's a sign of maturing. Because, you know, before we were just like, we don't know what we're looking at. Here's a huge neutrino detector, let's look. Now that we see signal, now that we see different kinds of signal we want to look at, and we have some clues as to how to optimize, you want different detectors. And I think that's not a bad thing. I think it's a good thing, right? That we know what we're doing and we want to optimize. But we need a global strategy. So IceCube, or neutrino astronomy, is not part of Astro 2020. This is the decadal survey in astronomy. It is not part of P5 either. We were mentioned in both, but nobody is taking ownership of neutrino astronomy. So the problem is we don't have a home. But I think what's detrimental here is that we don't have a chance to come together to discuss global strategies. And that, I think, is what's hurting us right now. Okay, now I'm going to zoom out even more from neutrino astronomy to multi-messenger astronomy. Okay, so here's neutrino astronomy, and then other messengers. And we are definitely anchored by gamma rays. Neutrino astronomy would not be here if we didn't have gamma ray astronomy. This is the current state. Everything we do assumes that gamma rays somehow change into neutrinos and vice versa. Okay, and other electromagnetic telescopes too. So then there's gravitational waves, of course. We try to do correlations, but it's tough. And then cosmic rays, which is often forgotten messenger. And that's because their aim is somewhere else probably, but also like neutrinos and cosmic rays have a deep connection. So I just put it there. Now this is, I think, what's happening now, but where we want to get to is something like this, where we are equal partnerships, at least a little bit equal. We'll never be as good as the electromagnetic telescopes. But if neutrino astronomy wants to do some independent things like measure sources that can only be seen in neutrinos and have more coincident sources detected with E&M telescopes, then we need a wide range of neutrino telescopes too. Like think about this blue circle, right? Astronomy has different telescope optimized to different wavelengths. Even for a given wavelength, they have different field of view, so different parts of the sky. So you have so many telescopes. If you want, I'm not saying equal, but a more equal partnership in neutrino astronomy, you can't just throw one neutrino telescope and say, hey, try your best. I think we need different specialized neutrino telescopes in the next era. Let me just end with one thing about the field of view argument. So here is the sky in equatorial coordinates again, I'm sorry. This is the galactic plane, and the x's are some sources along the plane. And here is the peak sensitivity for IceCube, which is in green, P1, which is in red, and KM3, which is in blue. So of course we see the whole sky, but the sensitivity is different depending on the region of the sky. And of course, depending on the time, this circles, but the point here is that we have complementary peak sensitivities. So particularly if there's a transient, right? If there is a galactic burst or something, it's important that we have different telescopes with complementary field of views, I think. Okay, so I'm gonna conclude here. So IceCube is a data-driven experiment. We are so background limited, and the more clever you can be about digging out the data, the better. And we are getting to a point where we have, what, 12, 13 years of data, and adding another year is 14 years of data. And people are like, well, that's not gonna discover anything new. And some people are even like suggesting like, let's lower discovery to 3 sigma, which is not a good idea, I think. That's not the way to go. The way to go is to understand your data better and be clever about how to use it. Different things need different data processing. Different aims need different types of data. And we need to be clever about it. And I think we can discover more with the data we already have if we're smart about how to use the data. Because again, we're buried in 10 to the 9 background. Neutrino astronomy, I think different needs are becoming clear. More and more, I'm convinced that a one-size-fits-all neutrino telescope doesn't exist. And I don't think that's a bad thing. I think it's a sign of a maturing field. So it's a good thing. However, I do think if we're going to do multi-messenger astronomy, we need to be able to make statements on our own as neutrino telescopes. And that's going to require different neutrino telescopes that are optimized in different ways. I'm not saying we need as many as the electromagnetic spectrum does. We'll never get that, but we can't just rely on one neutrino telescope to do all. And that's where I think the state of neutrino astronomy is. Thank you.
Thanks, Nicole. Questions? Frank, and then you. Okay.
Thanks for a very interesting talk. So it sounds like your working hypothesis is most of the neutrinos that you see from the Milky Way are associated with gamma ray emission and gets turned into neutrinos. If that is the working hypothesis, then what are you trying to learn? What is really the question you want to address with this data?
So I want to get away from that hypothesis, but I can't right now because we can barely see it. With gamma rays giving us a template, we can barely say we see it in a statistically significant way. We have no choice but to do that because we don't see anything on our own. That's the point. That's why I think for galactic neutrino astronomy, IceCube is not the right detector. and we need ocean or water Cherenkov detectors. And then I think we can start asking, how's it different, right? We can start making templates of our own from our own data, but we're not there
But
yet.
are there theoretical ideas out there why there would be differences? Why one thing should show up in neutrinos?
Well, yeah, I mean, the biggest thing is sources, right? If there are point sources in neutrinos, that should be subtracted. So that we don't assume any sources at this point, because we don't see any sources. So you can't really subtract things you can't see yet. But certainly there must be source contribution there. We don't have the telescope to tease that out, I think. Yeah.
At the time when we were discussing a facility in the Mediterranean, which at the time was Antares, Nemo, and Hestor,
yeah.
One of the main points was to have a facility in the northern hemisphere as compared to a facility in the southern hemisphere, like your facility.
Yes.
Are you saying that by doing a northern and the southern, we will be able to distinguish between galactic and extragalactic neutrinos?
Certainly, yes, that's part of it. But what I'm saying is the Mediterranean telescope, the water telescopes, they point very well, which is something IceCube can't do. Now, the trade-off there is they're not that big, or you can make it big, but the detectors will be too sparse for the signal, how much it travels. So you miss out on sensitivity. But galactic neutrinos are close. So, you know, hopefully we can point. And then, of course, the north-south divide, right? So do you have the Earth to filter out those muons or not? For all those reasons, KM3Net should do so much better in galactic neutrino astronomy. I think we are pushing the limits of what IceCube can do for galactic neutrino astronomy. And it has to be KM3Net, which is why I joined. Now the detector, I wish it were built already. It's a long building process. But I sincerely think that once it's built, like that'll be the definitive characterization of galactic neutrino signal telescope.
Okay. Unfortunately, it's going to be a very long process.
Yes, which is why there's a Pacific competitor now, I believe.
Thank you for a really nice talk. Let me ask you about the extragalactic sources.
Yeah.
So blazars are supposed to make, you know, if they're hadronic, they're supposed to make a lot of neutrinos. It's kind of surprising to me that they would find one, but not more. What's going on there?
I agree. And same thing can be said about GRBs, right? So if you asked anybody 20 years ago, what do you think would be the first neutrino source? I think a lot of people would have said GRBs, and now the limits are so tight. I don't know what's going on. Different theorists have different reasons, and different model builders have different reasons. I mean, yeah, it's puzzling. The diffuse flux is there. So there, did I put the, maybe not. I have this, you like that slide? I have this, oh, maybe I didn't put it. Oh, here it is. Okay, this is my favorite slide that is kind of very hand wavy, so take it as a grain of salt, okay? So we have this diffuse flux measured, extragalactic diffuse flux. Subtract out the galactic component, if you will. So we know the universe is emitting neutrinos, right, extragalactically. This is all and this is an old table, by the way, but this is all the analysis we do asking, can this population be responsible for the diffuse flux? And the answer is always no. And not just no's, but at most, it can be only responsible for 7% of that measured diffuse flux.
And how is that? How is that? Is that going from the gamma rays again? What?
So for this one, yes, because it's the Tulak blazars. So we said, okay, we have these blazars. I think back then the Tulak had 862 of them, and we said, okay, are these 862 places in the sky? Is that where the neutrinos are preferentially coming from? And the answer was no, right? And if it's no, we can set a limit on the emission. And that limit on the flux can now be turned into how much of the diffuse flux can you explain? So at most, it can explain 7%. Now, 0 is also allowed, but at most, it can be 7. And these numbers are pretty abysmal, which means that, and there's a huge caveat here that I'll get to, but which means that if there is a large population responsible for neutrinos, we have no clue what that is. And whatever our usual suspects are not responsible for a large fraction. So either there's hidden sources or there's just so many different things contributing to that diffuse flux that we can't pin it down, right? Now, the huge caveat for this table, which is the reason why I stopped showing this, is because it is very sensitive to the assumptions that we make for the spectral index, where we have an energy region that we're very good at, and then we get background dominated easily, and then we run out of statistics easily. So there, depending on this assumption, is it e to the minus 2, is it e to the minus 2.5, 2.7, that percent changes quite radically. So this is not a good table to show, so I stopped showing it, but I think it's telling that we've tried so many different sources asking if those are neutrino sources, and the answer is always no. But we know there's neutrinos coming because we measure them. So we have this flux of neutrinos. We can't localize it. We can't attribute it to any type of astronomical thing. And you're definitely not supposed to do this. But if you add these percentages, it doesn't even add up to 100, right? So it's mysterious, I think, because it's not the detector's fault, because we do measure the diffuse flux. I'm up for ideas.
Emily and then Carson.
Hey, so I was just wondering, why put a neutrino detector in the ocean when you could just put it in a lake or something?
Yeah, so you want to be like any particle physics detector, you want to get away from muons, atmospheric muons. So you want to be deep. So deep lakes, like Lake Baikal, definitely works. You also want to deploy so deploying these costs money. This is like really hard to put things deep in the ocean or deep in a lake. And at that point, it doesn't matter which one it is. It's just equally hard when you're that deep. And I suspect some of the answer might be there's more infrastructure in the ocean already to deploy things, possibly because of defense-related reasons. I don't know, but you know, not a lot of people are worried about Canadian submarines in Lake Michigan, right? So I don't know. Maybe that has something to do with it too. But so for some reason, the ocean infrastructure seems to be stronger or more deployment ready for us than lakes. Now, I think the Mediterranean, they did that all by themselves. There was nothing, and they engineered it from scratch, which is why it's so hard. Part of the allure of P1, which is why I joined, is that the Canadians have a huge infrastructure off the coast of British Columbia, where it's basically plug and play. So you can just give them your detectors and they will go plug it in for you. And they already have cables to shore with power and comms and everything. So there's different optimizations, yeah.
Yeah, then you have society, 3,000 meters.
3,000 meters. Imagine deploying something 3,000 meters from an unstable surface of the ocean, not ice. A solid ice is okay because you can stand, but rocking boat, yeah, that's hard.
Yeah, thanks for the nice talk. I was wondering if you could say a few more words about the status of P1 and what makes it unique.
Yeah, so the plug and play definitely makes, I think that's the most attractive thing for me. And certainly I want a Northern Sky water tank up detector for galactic neutrinos. So that's what's attractive to me. So KM3net is a good experiment too. And so I used to wonder why have both? And I think at this point, I'm okay with both. The more the better for reasons I explained. The other thing is a lot of the development of the hardware and the triggering system, they're all very modern. So this is like a modernized, what our selling point at least is that this is a lean, mean neutrino machine, right? That it's a modernized mainboard, modernized electronics, modernized trigger systems. So that, you know, this is not, so for example, KM3net and IceCube, these are all like technologies that's at least a decade old. And these technologies move very fast. So if we can do better triggering, better waveform recording, better algorithms on board, we can lower sensitivity. That's kind of the selling point aside from that. Yeah.
Yeah, I have another question about the like water train cup
Yeah.
detectors. So in an ocean, that's a slightly more like dynamic system
Yes.
than in ice.
Yes.
So like how do you plan on, I guess, accounting for that? And is that an extra challenge?
It certainly is. So the ice at 3 kilometers down is stable as can be, right? Nothing changes. There's no temperature drop. There's no, or temperature swings. There's no current. There's nothing living. And the deep ocean is not true on all 3 of those things. So the background changes over time, which is something we need to combat. So for triggering, we have to be a little bit smart about the background weights of the time, also the current, which way the current is going. Also, if the whole thing sways, right? If the whole detector sways a little bit, that, you know, there's some timing resolution that you need to think about in terms of calibrating where your strings really are in a moving environment. So there's some acoustic calibrations we need to do, you know, repeatedly to say, okay, at this point, the detector looks like this. So there's a lot of extra challenges, I'd say. Also deployment, obviously. Like if you can stand on a solid thing and drill, it's actually much easier than trying to lower something into a liquid that's moving and you're sloshing on top, right? So yeah, I don't know if that's a good explanation, but yeah, the challenges are very different. Yeah.
Thank you.
Oh, yeah. There's a lot of bioluminescence in the ocean, which we don't have in ice. There's nothing living at the South Pole naturally.
Hi, real nice talk. I have 2 curiosities. The first one is about a neural network model that you are using.
Yeah.
How much data do you need and for how long time you need to train it?
Yeah.
And the second one, it's just a curiosity. Do you think that someday in the future, the climate change will affect the experiment?
Okay, so first one, I know there's like, we simulated like what, I think 10 million to 100 million events, depending on the event types. We were concerned about some things more than others. So we have specialized Monte Carlo that we trained the neural network on. So this is so for reconstruction, you just need a lot of different cascades that trigger because that's representative of your sample. For the filtering, the data filtering, we're worried more about edge cases we're not accounting for, right? Like we want to make sure we're filtering on the right thing. So like I said, if you have 10 to the 9 backgrounds and, you know, 0.00001% does this, right? We want to make sure we filter that because that's going to overwhelm the signal. So that was more specialized Monte Carlo. So I think that was a lot more events we generated. Time, I don't know, sorry, I'm not expert enough to comment on the time it took. Global warming, yeah, global warming. So we are inland Antarctica, so the ice sheet definitely does move, but not at the rate. I mean, actually, if you're at the South Pole, the pole marker actually moves every year, and that's not because the South Pole moves. That's because you're moving on the glacier. So there is that, but that's again in the astronomical things, it's negligible. It's hard to melt 3 kilometers of ice, I think. So I don't think it's a time scale I need to worry about. And then, yeah, I don't know if there are unseen considerations from global warming. Yeah.
One last question.
Thank you. Thank you for the very interesting talk. I was wondering if, given the sensitivities of detectors to neutrinos at different energies, can you make predictions about the absolute density of neutrinos at different parts of the universe, or like as opposed to just the relative fraction of neutrinos coming from different places?
Like how much neutrinos should we expect overall from the universe?
Yes.
So we do have a diffuse measurement. I did kind of not talk about that, but we do have an all sky diffuse measurement. Which just means that I don't care which direction you come from, how much signal is above my background, and that's kind of the flux, right? Let's see if I have that plot. I probably don't. So the interesting thing for IceCube right now is that I don't have it, do I? Maybe I do. Yeah, maybe this is kind of it. So this is the astrophysical diffuse measurement. So this is E square flux again versus energy, again, log. I don't know if you can see, there is this red line, there's this gray line, there might be a pink line in there too. Anyway, these are all the measurements of how much of a signal above background do I see in IceCube. And you can see that they don't particularly agree about the flux characterization. So these are different channels of analysis. So they're IceCube data, but they don't look at the same events. So you can filter it out in different ways and say, I'm focused on things that come from the northern sky, or things that are cascades, or things that start in the detector that is more background free, or whatever, and do this measurement. Right now, we're not sure if they agree or not to each other. In both the flux level and the spectral index. Now, there could be many good explanations for that. It could be that different regions of the sky, like you said, have different densities, right? Different fluxes. So if you only look at half the sky versus the full sky, maybe you get different answers. Maybe there's local sources, strong sources that somehow we failed to look for it, but is making this anisotropy in the sky. It's possible some of these have different flavor targets. So maybe, as unlikely as it is, maybe the neutrino flavors are different. And a lot of, also, maybe not this one so much, but some of the analyses, like they definitely have a favorable energy scale where the error bars are small. That's different. So maybe at different energies, we're looking at different kinds of fluxes, and who knows, right? So this is called the diffuse flux, like global fit. We're entering an era where we're not sure what's happening, and the data is enough that we think maybe, we're not. So the neutrino astronomy is really hard. So the first thing you do is assume like the simplest model possible, which is an unbroken single power law. And you say, what is the best single power law I can fit in my diffuse flux? We're getting to the point where I think the single power law doesn't explain all the data anymore, at least in some channels. Maybe in other channels it does. And now you're starting to argue like what is happening here. This is not what I do at all, but this is, I think, the other exciting thing about IceCube is characterizing this diffuse flux. And this is a statistics hungry analysis. So before I said, 13 years, we see nothing. 14, what difference does that make? This is an analysis where, each year of data might surprise us. So this will improve with more data, I think, and we'll resolve it one way or another. But I think this is also one of the other frontiers in IceCube that you should keep an eye on.
Very interesting. Thank you.
Well, let's thank Naoko again.
Thank you.
Thanks for the great talk.